All right, so hello and welcome. Howdy, here we are. Where the next question we're looking at is Palindrome Partitioning 2, hard. I don't know anything about this question, so we'll see how this goes. But this should be curious. So yeah, let's get into that. So yeah, here we go. Palindrome Partitioning 2, and this one we're gonna turn off. Okay, we'll get right into it. So, given a string S, partition S such that every substring of S, the partition is a palindrome. Substring S, partition S such that every substring of the partition is a palindrome. Okay, return the minimum cuts needed for palindrome of partitioning of S. Don't think I fully understand. So, okay, so we can minimum cuts needed. Output 1. So palindrome partitioning can be produced using 1 cut. A 0 cuts. A B 1 cut. 2000 S lowercase English letters only. So what about some other examples? Like what if we had like a what if we had like A B C. Like let's do A B C something like this. How many cuts do we need to make it a partition this into palindromes? And then, so every substring is of the partition is a palindrome, and the minimum number of cuts you need for palindrome partitioning. So, obviously, we could do the maximum is n, right? Size of the string. Could do just 1 cut for every character, or n minus 1, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 cuts, right? N minus 1. Or size minus 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So size minus 1 is, we could always make that many cuts to make these palindromes. However, there may be a smaller number of cuts we could use. So in this case, this is a palindrome. AAB is not. AA is not a palindrome. So there is an algorithm called Monikers Algorithm we talked about previously, where you can count the number of palindromes that you have. Palindrome counting, palindrome substring counting, I think it was what it was, and you can do that in linear time. It's a really interesting algorithm. I don't remember it offhand, but it goes something like this. Like you have, as you move right to left, you have like an inner radius type of thing. So you have some index, and you have some R amount. And basically the idea is that the things to the left you've seen, apart from this inner portion, those will match the things to the right to a certain extent. That's the idea. There's sort of these like palindrome sub-palindromes within a palindrome, right? And that's kind of the idea, is that you can use, as you increase from right to left, or left to right, excuse me, you can consider more, I think it's the longest palindromic substring. That's what you would do, is the longest palindromic substring. But what we can do, we can use Monikers algorithm to find the longest palindromic substring from left to right, starting at a particular index, right? And then we can then make a cut there, and then find the longest palindromic substring at the next point from there. So yeah, so that's the idea. We can use Monikers algorithm to find the longest palindromic substring. It wasn't counting palindromes. You could probably also use that to count palindromes too, by the way, because each of those each palindrome you find as you go, you can sort of count a certain number of palindromes as well. So monikers can also be used there too. It can be used to find the longest palindromic substring. It can be used to count palindromic substrings. It can also be used for this problem here. So let's see if I can remember Monikers algorithm though from memory from a few days back. But here you see a palindrome, and I think it ends here. So there would be 5, one cut there. I don't think you can have a better substring here. What's interesting is 2000. I don't know if you could actually use monikers to do this Monikers algorithm. One of the problems, one of the challenges is this is a palindrome, this is a palindrome, this is not a palindrome, but you wouldn't cut it here, right? You can keep going to find a palindrome. Yeah. So I think what you'd want to do is, as long as your longest palindromic substring contains, so that's tricky. I don't know if you can even use monikers. I mean, I think you must use monikers for this. I just don't remember it offhand. I'd have to look at it again. Well, I think I know what it does. I think I get the basic idea. The problem is, I would say something like this. Like you would have a previous longest palindromic string up to that point, and if the next longest palindromic string doesn't contain the previous one as a substring, that means the previous one you have to make a cut there, and then you have to, I guess, start your algorithm trying to find the longest palindromic substring, which you could. I think the next longest palindromic substring, not even longest, just next palindromic substring. So AA contains A, AAB, you'd have to make a cut at AA and start at B. And then you get to BA, AB, but you wouldn't make the cut at A. You'd wait till you get through AA, BAA. There may actually be an algorithm to do this that's like not as difficult as I'm thinking it is, but I think not using monikers here is probably a mistake. Like it's probably monikers is the way to go. Let me just see. How are we doing on time? 8 minutes. I don't actually have a solution for this. I don't have a solution for this, man. Nope. No, sir. No, sir. Yeah, I was thinking about like different possible, I'm not thinking, but I'm thinking maybe there could be possible like a DP solution of some kind, but probably not. You know what we can do? We can try to find the longest palindrome starting at, the problem with trying to find the longest palindrome starting at an index, the problem with that is even though it would be linear, we don't know how far we should go before we stop. That's kind of an issue. Because like maybe we just go double the length, but even that, like this becomes a palindrome all the way out here. That's not really ideal. Oh yeah, I forgot. Yeah, so the way that you do it normally is you have these quote unquote onions, right? And you create this onion by either moving to the next character, or take a character to the left, character to the right, and check if you have a palindrome, right? So this becomes a palindrome, and then this value to the right, like in other words, if you hit off the edge on the left side, then you would move to the next character here, right? So now you're outside of your onion over here, and so this immediately breaks also. There's no palindrome here, so you move here. This breaks, no palindrome here. These just all just kind of break one after another. But what's interesting is like there's sort of like this onion creation you do, and then you process sub onions if you happen to be moving to the right. If you break your onion, so to speak. But yeah, you have your longest palindrome here. That's what we're looking for, longest palindromic subsequence, or counting palindromic subsequences. Not subsequences, but substrings. So I think the deal with the onions have some issues here where I don't know the solution offhand. I gotta think about this here. What do you do? What do we do? What does Monikers actually do? I know it does something with substrings. I don't remember. All subpalindromes in O of n. Okay. So it is all of the. So suffix trees in fast LCA can be solved in linear time. Sufficiently simpler, has less hidden constant time in time and memory complexity. Moniker. Alrighty. There's a slow algorithm. There's a trivial algorithm. That's that quote unquote onion creation type of deal. So Monikers uses, there's D1 and D2, which are similar to each other. One of them starts at, for even palindromes, the other one performs, there's even palindromes, the other one is odd palindromes, and excuse me. And actually, I had figured out one way of performing this algorithm with just the explanation. So the idea is that if you find a palindrome, then inside that palindrome there are other palindromes, subpalindromes. So it says, want to calculate d sub 1, so let's start with d sub 1, so it's d sub 2. Start with d sub 1. If I is outside the current subpalindrome, I is greater than R, we launch the trivial algorithm. I is greater than R, yeah. So there's some radius of your, there's borders L and R, the rightmost found subpalindrome. Okay. Excuse me. Palindrome with maximal R. Set L equal to R0, R equal to -1. Want to calculate d sub 1 of I for the next I, and all the previous values in d sub 1 have been already calculated. We do the following. If I is outside the current subpalindrome, we'll just launch the trivial algorithm. So I guess one way of doing this is maybe we can find if there's at least one. We want to find at each index the largest. We can use Monikers algorithm to find at each index. We're going to create a map at each index, the largest palindrome beginning at that index. That's what we want to do. So this is going to be all. We're going to find all the subpalindromes, and what we're going to do is find the longest palindrome from each index from left to right. So what that would look like is if you found a palindrome with a trivial algorithm, then what that's going to be is, and then we're going to process that at the end and make our cuts. The trivial algorithm we can use to find a palindrome, and that gives us our left and right, our L and R values. And for all the values from the left side to the middle, we can update the largest palindrome. So how far out, which index it ends at, the largest palindrome, which index it ends at. So like we had over here in our example, AA, BAA, when we expand AA, BAA, we can update A to all the way to the right. So it's 1, 2, 3, 4, 5. So it would be 0, 1, 2, 3, 4. Let me just check my phone. What was I saying? Sorry, I got kind of stuck. Not stuck. I wanted to respond to something. So, what I was saying was, so we can update all of the values to the up to that point, left to right. Now, I don't know if that's a good idea. I'm thinking about it because that might be quadratic time if we did that. What we could do is when we break the right side, right? So we have so we're going to maintain borders of our rightmost largest palindrome, right? That's the idea. If we break the right side, that's when we should update all of the values inside of that palindrome. Yeah. So that's in this case. This one. So when I is greater than R, once we're going to start launching the trivial algorithm, I is outside the current subpalindrome. As soon as I ends up outside the current subpalindrome, then we're going to update all those values, L to halfway through R. I think if we do it that way, then we can get the longest palindromic substring starting at a particular index, and then we can use that to make our cuts. So first question about that though is I don't know if that's actually I don't know if that's actually the best way to do this, because it may be that like different, even if we did use monikers to do this properly, another question you have is like, how are we doing? 20 minutes in? Even if you did do this properly, another problem is like, well, which cuts should you make in the first place? Like even if you got the maximum palindrome, right, from left to right, you actually want the optimal number of cuts, the minimum number of cuts, not the most per cut. Like a greedy algorithm, even if we did that pre-processing, a greedy algorithm actually wouldn't necessarily be correct there, which is what I would have liked. I'm going to go ahead and sit down because because of I gotta think about this. Even a greedy algorithm is not necessarily what we want. Excuse me. Now we might be able to use a like a jump frog, quote unquote, algorithm, where now we have this. Basically, we want to get the minimum number of jumps to the end of the array, and at that point, at each index, that would give us the amount we can jump. I think what we can do there is then we can use there's like a sort of a breadth first search type of algorithm that we can use to optimize the number of jumps required to get to the end. Yeah, that's an interesting question and an interesting algorithm. I've seen that before. That's kind of fun. So we could actually do that way. How many jumps we need, and every value always has at least a 1, so you can always jump at least 1. But the way you do it is you would it's a tricky algorithm, but it's linear. But the way it works is you take it's a kind of a breadth first search. So excuse me. So the first step, you get like an end of your range, and then you add to each index as you loop over the indices left to right, you get another value for the range, and you have excuse me, yeah, then you update the beginning of the range to the previous ending range plus 1, and then you loop through that range and do the same thing, and you do that every time, and you kind of step through, and you count how many jumps it takes, the minimum number of jumps. Yeah, so you can actually do so this will work. If we can get it to work, it'll work. Pretty interesting question. What's that, 23 minutes, 24 minutes? So I don't know, like the tricky thing here now is that we need to use monikers to set up, and hoping that it's linear, set up the number of to count the size of each palindrome, the largest palindrome at that particular spot. So I think you could initialize the array to all 1s, start off with that, and then run the trivial algorithm, your onions, and then once you're outside of I, then you take that left and right, those borders, update all the values of the largest palindrome, and then I think you run the trivial algorithm again from there. Now, what's interesting is you can optimize slightly when you're not outside of the trivial algorithm. You increase D1 of I consecutively and check each time the current rightmost string is a palindrome. When we find the first mismatch or meet the boundaries of S, we'll stop, and that's when we perform our update, I believe. In this case, we finally calculated D sub 1 of I. After this, we must not forget to update L and R. So yeah, you find the boundaries, you update L and R. R should be updated in such a way that it represents the last index of the current rightmost subpalindrome. True. Consider the case when I is less than or equal to R. So we increase D of I, and then yeah. Consider the case when I is less than or equal to R. We'll try to extract some information in the already calculated values in D sub 1. So let's find the mirror position of I in the subpalindrome L of R. We'll get this position J, L plus R minus I. It's kind of tricky, but there's so what this is referring to is a couple things here. The values for D1, I think these are telling you, what does D1 tell you? D1 and D2. Yeah, so the idea is at each index we know D1 and D2, we know the size of the palindrome there at that position. Find the values D1I and D2I, denoting the number of palindromes accordingly, odd and even length of centers in the position I. Yeah, there we go. We do want monikers. It's actually we can use monikers and then just update the result at the end to update left to right. So we can use monikers and then just update the array again when we're done to or update another array. We could create another array too. We could just create 3 arrays. It's fine. Or create a new array that gives us the quote-unquote leapfrog array, and then we can perform a breadth first search on the leapfrog to give us the minimum number of jumps required, and that will tell us the number of jumps should be exactly 1 more than the number of cuts we need. So that should solve the problem. Solve the question. The question that I have, the problem I have though, is how do we write monikers in a way it's good, I guess. So there's the trivial algorithm is sort of the onion that's expanding, and then the idea is that if I is in this onion, we have L and R, the left side and the right side. If I is in the onion, that's when we might want to use a subpalindrome, and that's this part of the algorithm, which I just don't remember. Try to extract some information already contained calculated values. The mirror position of I in the subpalindrome, so J is L plus R minus I. So you add L and R, and then you subtract I, and that gives you the mirrored position. That's J for where I is. And calculating that's kind of peculiar, but basically you could imagine as I plus J should be equal to L plus R. So then you could just subtract I from both sides, and you get J. That's like the easiest way to explain it. And we check the value of D sub 1J because J is the position symmetrical with the I. We will almost always can assign D1 of I to D of I of J. Illustration of this, but there is a tricky case. The inner palindrome borders the outer one. The symmetry, it's not guaranteed, just assigning this value being correct. Don't have enough data to state the palindrome in this position. Should restrict the length for a palindrome for now. Assign D1 to be this value to handle such situations correctly. After this, we'll run the trivial algorithm which will try to increase D1 while it's possible. Illustration of this case, the palindrome with center is restricted to fit the outer palindrome. So what's being referred to here is in if we're inside of our larger palindrome, if I is inside, we can use the mirrored position, and we have to keep track of where the position is and where L is, and we would say if the palindrome goes outside of L, then we have to cut the we have to restrict, as you see, they have it here, r minus I plus 1, have to restrict the size, which is similar to, so we don't go out, so alternatively you could say, like, if the value on the mirrored side, if that palindrome exceeds the bound, or exceeds r on the right side, then we have to restrict to only the characters up to r, and then we can continue the trivial algorithm from I and increase it from there. That's the only thing. So it's pretty simple. It's if to use I to create an onion, if you're inside the onion, you're going to take the mirrored value to update part of the number, and if you exceed outside, if that update would push you outside of R, outside of your current onion, then you'd layer more layers on your onion, and you continue, and you go I again. If you go outside of your onion somehow, end up going outside of it, then you create another onion, and that's it. That's the whole algorithm. It's pretty straightforward, pretty simple. So we're going to try to, and you do this for even indices and odd indices, and we're going to basically, yeah, so we'll do Monikers algorithm. Monikers. So we'll say even and odd, so we're just E and V, we'll call it. So we'll use these two arrays, integers, E, V, integer arrays, and this is going to be s.size and V of s.size. And we're going to say the trivial routine looks like the following. It would be, it's just a for loop. So we'll do, so there's a loop we perform, int I equals 0. S.size plus I. And we're going to say there's L and R. We'll start off with. So we'll do these two. We'll do two routines to get L and V, or E and V. But we'll do int L equals 0, R equals 0, or -1. It starts off with, and we'll say, so we'll do even first, or odd. We'll do odd first. Oh, E and O should be even and odd. We want, so the trivial algorithm would be if I is greater than R, and we do the following. I is greater than R. We're going to run the trivial algorithm, and we're going to say it's going to go something like this. The trivial algorithm would be a for loop of some value k with a number of characters, and really it's a while loop actually. Well, we do for loop. That's fine. It's going to be I minus k is greater than or equal to 0, and I plus k is less than or equal to. So the size of the onion we're starting off at. I guess we could start off at 0. Well, you already have a palindrome. We have to initialize both of these too. The palindromes are always at least size 1. So the odd palindromes, odd of I is always going to be at least 1. Odd of even of I is always starts off at 0. And yeah, so you're going to increase from this point. So I minus k, I plus k. Just thinking, so for the odd case, and I plus k is less than or equal to, or is less than s dot size, and we're going to plus plus odd of I. That's kind of it. It's really just a for loop here. That's really it. This inner loop. So we would say O of I minus k is equal to O, or not O, S of I minus k is equal to S of I plus k. And you can start off with 1. I think it's that simple. Now, we also want to update I don't know, there's probably a way to do this that's reasonable. We also want to update some other parts. How are we doing on time? 36 minutes? Okay. Also want to update L and R. So if R is, so if I plus k is greater than or equal to R or greater than R, then R equals I plus k, and yeah, that's right. And L equals I minus k. That creates your onion. Now, if we're less than or equal to R, then we're going to use our sub palindrome, and we're going to say, we said the similar thing. If we're breaking to the right, so we say int x is going to be O of the mirrored value, so we're going to say j equals, we said it's left plus right is going to be equal to I plus j, so we could just subtract I to get j. O, x is O of j. If I plus x is greater than or equal to R or greater than R, then we're going to set int, or yeah, we actually update x, because x is just going to be this value, but x should then just be R minus I plus 1. And then we're going to run the same routine here. Run the naive algorithm again. Yeah, trivial algorithm. I'm going to duplicate the code here only because I think we could write a lambda expression to do this, but it's just we have multiple variables to modify. We could write the trivial algorithm, or onion algorithm. I like to call it the onion algorithm. Create layers. And we're going to take L and R. We're actually going to modify L and R. We're also going to modify O and E. And I think we're going to basically put this here. So I, constant I, some index that we're going to create the onion at. Onion at, onion, S, L-R-O-E-N-S, Yeah, that's fine. That's fine. I plus k greater than r. Update r and l appropriately. Yeah, okay. So we can call our onion of I. It's so much cleaner. Just putting the onion routine as one call here. Same thing over here. Oops. So we set x equal to r minus I plus 1. And now it's slightly modified though here. We would say k, int k. We'll start off at 1. Right, so the onion is just initially 1. Here we could say the onion starts off at x, right? Or it should be x plus 1. Yeah, we do x plus 1. That's fine. So this would be alternatively I and x plus 1, right? And then now this would increment to, we'd increase k and also O of I. So O of I would be set to k. That's one of the tricky things here. Now here it's a little bit different because we could say at the end of this, we could just say O of I equals k. That's what we should do. Over here, same thing, as O of I is going to be equal to k. So the x plus 1. It really should be k minus 1, right? If k starts off at 1 and this fails. So that's a tricky thing, is how much is already set. How we want to use these two things to do this properly. Also, this is taking a while. This is probably going to take us like an hour because I don't really write Monikers Algorithm too frequently. So there's some things to be said here. Yeah, I would say k minus 1 is actually correct. Because if we start off at k is 1 and it fails, k really should be 0. So it is k. It is k. If k is 1, k can start off at 0. That's fine. And obviously it'll increment k once to 1. K of 0 shouldn't fail. It'll increment k and then try again. Now if that fails, k would be 1. And that would be it. Or if it fails at 1, then that's the correct amount. If we go to 2 and it fails at 2, k would be 2, and that's also still correct. Now the size of the palindrome is we're saying how many characters from that particular point. So it could be 3 characters out, or no, how many layers of onions actually is what we have, which is kind of awkward. Basically, 2 iterations. Yeah. So with the odd, with an odd onion, it's a little bit different. We could just say how many layers it was. We could also do this, odd or even. We could just say how many layers and yeah, actually the odd onion and the even onion are a little bit different too. An odd onion. That's another issue. Trying to write this code in a way that's like it works nicely. We can use, it's kind of malleable. We can use it for multiple things, I guess, without just writing these loops all over the place. Duplicated loops. Yeah, I mean, you can start k off at 1. That's fine. This just tells us how many loops failed or how many loops succeeded. So we always, for odd loops, we always have at least one loop. What about like, so 0, 1, 2, 3. If we get to 3, right? So k is 3, we fail at 3, we get 0, 1, and 2. That means we have 2 characters in addition to the middle character. That means 5 characters total. So it's 2 times this k plus 1 is the odd onion. What's interesting is here you would say odd onion of I x plus 1, which would be x is r minus I plus 1. That's how many. Now that tells us how many characters we have. See, that's not quite what we're looking for. So we actually want, well, is that what we want? Just thinking. If this x value is, so we actually want the total number of, we actually do want the total number, like, of characters at that point. We don't want like a halfway done thing, because we're going to use the number of characters to figure out how big our if we're going off the side of the onion or not. If we have x characters, so x is the mirrored onion. We know how many characters that is. If we oh no, well, no, I'll go back. So confusing. I already took that into consideration. That's so awkward. How many characters between R and I? Yeah, no, that's fine. That's okay. We set X to that number of characters. That would be, excuse me. We're doing this correctly. It's confusing, but we're doing it right. If we had like B, and there was 3 there, A, B, C, B, A, B, C. That's 4 characters. Let's just pretend for a moment I was like, I don't know, 10. And where does that put R at? B, 10, 11, 12, 13. 13 would be ABC. So you have R is at like 13. R minus 10 plus 1 is 4. Now that's not exactly correct, because K would be 4 actually, yeah, because you'd have the first iteration, second iteration, third iteration. The fourth iteration, you'd actually fail when K is 4. And do I plus 4 would actually be 5, the 5th character that would fail, but K would be 4 at that point. So that's really confusing. It's from the center. It's the number of characters from the center to the right, including the center. So then you'd want to go to. You could just start at X. I think that's fine. Where it is, just start from where it's at. That was kind of what this whole ordeal was about. Was trying to figure out what this number should be, and how do we set up the odd onion routine here. That's so confusing. That's it, actually, by the way. And then you eventually set, so yeah, you set that particular value at the end. Now, is K the right value? Do you do I plus K? Yeah, that's fine. It's greater than R. Update R and L. Yep. Yep. I minus k, so it's I plus k to the right. 1, 2, 3. Let's see, 1, 2, 3, 4 characters, including the middle one. If I is 10, then you end up with 4, 14, 10, 11, 12, 13, 14. That's 5 characters. That might be too far to the right. Yeah. 10, 11, 12, 13, 14. 10, 11, 12, 13. That's 4 characters. So confusing. So confusing. Also has to do with things being odd and even as well. If you have 3 characters from that point, you include I, and then you'd add I, 2 more to the right. Do 10, 11, 12. So yeah, you actually would do 1 less than I to get all the indices. So that would be R, would be the index of the last character. That's the deal. Okay. So that's how you'd process the odd. I think that's it. I think it's monikers for the odd portion, and then you'd also process for the even portion. You have the odd, quote unquote, odd onion and the even onion. It's very similar. Left is 0, right is -1. Just start over again. So it's a lot of code, but gets the job done. So the even onion. Now, the even and the odds are quite different from each other. Not crazy different, but they're different. The deal with the even is that you start off with 0, and you're going to you don't, the index that you start at, it's a little bit different. You're actually, the characters are right next to each other, so they're not. So they sort of have like a whereas with the odd, odd onions, the middle character is always a palindrome, and then you just layer on top. Well, you don't have a middle part that you layer on top of when you're doing the even onions. So the layering is like there's still space between the characters, but they start out at different points. So I think the even palindromes, you have an index I and then I plus 1, I and I plus 1, and then it would be, or if you had some I plus 1, then you have those are the first characters. Then you do I minus 1 and I plus 2. So the distance between those I plus 2 minus I minus 1 gives you plus 1 at the end, gives you 4, right? That's what you want, range of 4 inclusive. But it's not just I plus k and I minus k. It's I plus k plus 1 and I minus k. Yeah, it's something like that. And yeah, so you base it on the left side. So when k, and this also you start off at 0. So k is 0 and I is 0. That's the first iteration. Yeah, so k should start off at 0. And yeah, these iterations are a little bit different. So if you if you succeed with an even onion, if k is 1 and you have a success, so k is 0, you succeed, you add 1, k is now 1, that's actually 4, you fail, k is still 1, that's correct. So that still works the way we've set this up. But now the left and the right side is the left side. So it's not it's I plus k plus 1 is the rightmost value. And it's actually this one. I think these we subtract k, subtract 1 from k in all these scenarios. Yeah. This is the index where we actually, the last index that has a character on it, so that's why you subtract k from 1. I didn't really think about that before. The last one that was successful was actually I plus k plus 1 minus 1. So plus 1 minus 1, which is just I plus k. So this one is I plus k. And then you do the other direction too. Yeah, this one's a little bit weird. This is also plus 1. It's I minus k, where minus k minus 1. So k minus 1, we input k minus 1 in here as I minus k minus 1. So we actually have a plus 1. So a little bit confusing, but I'm fairly certain that's what works with the even onion. So you have an odd onion, we have an even onion. We didn't really, I could probably double check this again, but I didn't really do that to make sure it's correct. About an hour in, odd onion, even onion, perform the left, perform the right. So the even onion, we start off at 0. And also r minus I plus 1, if we exceed to the right, a certain index, how many characters do we add? L plus r minus 1. So the number of characters, if we have even, it's actually going to have 1 extra character to the right, I think. Like if we have 2, then that means we have, if we have 2 characters, which is 1 iteration. 1 iteration puts us 2 characters to the right. 2 iterations puts us 3 characters to the right. 2 iterations would be like 3 characters for the odd onion. So it's actually x. How does it work? You would. So let's say it's 1, right? Let's say we have 1 for even. And basically, I'm trying to get the right condition for this and this. This is tricky. Tricky thing. What's I plus x when x is an even number? Let's say if the number is 2 to the right side, that would give you 3 characters. If I was like 5 and x was 2, you go 5, 6, 7. So the index would be 7. So it would be 5 plus 2 minus 1. Oh no. 5 plus 2 would put you at 7. That's confusing. The odd side, I think, though, is not correct. We have I plus k minus 1 it should be. So the odd side, if you had 2, we're saying that's 2 in addition to the 1 in the middle. That also would be 3. Oh no, so these actually end up being the same. That's kind of weird. But these should be the same too then. So confusing. If k is 0, it doesn't fail. K goes to 1. If k is 1, and it doesn't fail, it goes to 2. So we would have 2 characters from the middle. If we had 2 for even, we would have actually 3 characters. So even has 1 more character. I'm so confused. I am so confused. 3 characters. So odd gives you 3 x. However many characters you have from the odd to the right is. That's how many characters. That's a it's a sort of substring starting from the odd to the right. That many characters. Even on the other hand is not quite the same. So if you have 1, you actually have a substring of 2. You have 1 additional value for the even. So that's why you don't have to subtract 1. No. So actually you should. Why are you subtracting 1 at all? Wait, what is going on? Why are these? What are we doing? It's so confusing. I think these parts I got right. This just has to do with, so I plus k minus 1 greater than r. R is some index. Let's say the index was 9 and we had 5. So we have 5, k was 5, 6, 7, 8, 9. K would be 5 to touch 9. And we'd have to do greater than that, so it'd have to be 6. It'd be 10. I have to have k is 6. 6 characters from index 5. If we add those two, we get 11. We should subtract 1. Yeah, for some reason we do subtract 1. But if k was 6 for an even, then that means we'd have 5, 6, 7, 8, 9, 10. So 6 at even would put you at 5. We have 5, 6. So if k is, it's so confusing. I think the problem is that k is not the number of characters to the right. K is how many layers we have, right? The number of characters to the right is going to be 1 more than the number of layers. So I think that's also true for well, if we have number of layers, it implies 1 more character for the even side. So we feel like we need to actually subtract 2 over here. Like that. That's the thing that's way too confusing. I don't know why it's so confusing. I don't know. I'm struggling. I'm having a hard time. This is like way more involved, more difficult than it needs to be with this problem. I don't know if I'd be able to figure this out again too, like the indices dealing with this. All right, we'll try again. So what's the issue? We want to know, after we figure out how many layers, k, of an even onion, we want to know if we have exceeded the right bound, starting from I. So we're adding in, so k gives us the number of layers. First layer gives us 2 characters. Second layer gives us 3 characters. So If k is the number of layers, k plus 1 is the number of characters. Okay. So I is an index plus k plus 1 characters minus 1, so I plus k, puts us that's how many indices to the right we are after we've counted that many characters. So it's I plus k, that's the index that we're at. If that is greater than r, yeah, okay, that's all we need. For the odd onion, the number of layers we have tells us is actually equal to the number of characters we have from I. So if we have 5 layers, then we have 5 characters from I, and that gives us, if we do subtract 1, we get the index. Yeah, so we did this right. Okay, I don't know why I'm so confused about this though. And you're going to update R to that index, and similarly here. So we did this okay, but I just seem so confused. Well, I think the part I'm confused about is over here. Now we say X is the number of layers we have from I. So again, even the number of layers gives us exactly the number of characters. So we have to subtract 1 to get the index. And on the other side, for the because we're comparing indices to characters. On the other side, when you have and this will update to the number of characters. So now this is tricky. So for the odd side, the number of characters difference between R, the current R, and I is R minus I plus 1 inclusive. And the even side, there's a 1-to-1 correspondence between the number of layers and the number of characters. However, on the even side, we have to actually take X is the number of layers. The number of characters to the right you have at that point is number of layers. Number of characters to the right would be, if you had 3 layers, you would have 4 characters, right? 1, 2, 3, 4. 4 characters. 3 layers, 4 characters. Layers and characters. 3 layers gives you 4 characters. So add 1 to the number of layers to get you the number of characters. Subtract 1 from the number of characters to get you the index, which is actually X. So that's actually correct already. We don't need to subtract 1 for I plus X. That tells us how far we are out, the index. And the number of characters, now we're converting that to layers. 3 layers gives us 4 characters. So that means add 1, to get the number of characters, to add 1 to the number of layers. To get the layers, we have to subtract 1 from the number of characters. So we actually have to subtract 1 here. Oh, that is so confusing. Yeah. That's really confusing. All right. But this is Monikers if you can get the indices right and you don't get too confused. What we need to do now is, what's it saying? It's been a while. It's been some time. Now we need to see if Monikers is correct, if we're getting the right values for D1 and D2, or O and E. Yeah, we're gonna run this on some things. Okay, we're gonna say I is I. We're gonna say O of I. So O of I. And E of I. It's E of I. And at the end, we're going to return 0 to test. Yeah, and we're going to run this on, I don't know, A, B, A, B, A, B, A, C, B, C, D, F, B, A, C. Something like this. We're not going to do A, A, B. Okay. First is this compile. Let's start with that. Yeah. Okay. So odd and even palindromic substrings. That's what we're looking for. So 0, odd is 1, even is 1. Correct. 1, odd is 2. Even is only 1. True. 3, or no, 2. 1, even 0. 3, at this one, is ABA. Correct. Oh, but this should be actually AABAA. This one is not large enough. This is wrong. So some error here on the odd portion. E is 0, which is correct. Oh no, sorry, it's 3. 3 is right. 1, yeah, no, 3 is right. I'm sorry, I got that right. 4 gives you 1, correct. But E is 3. Oh, that's interesting. 1, 2, 3. Whoa, didn't even see that. Okay, I think it works. I think we did it right. Monikers is not too bad. It's relatively simple, but it's definitely really confusing getting these indices right. I mean, I thought about that for a while. We have our odd onion and even onion subroutines, and we got to increment and decrement values ever so slightly. I don't know. I guess we got it. Anyway, so yeah, so that's fine. So now we have odd and even. Now we say create jump array, and we'll say jump. So int jump of size. So this is going to keep going. For int I equals 0, I is less than. So we could say, yeah, for a given index, we're going to say, yeah, for int I equals 0, I is less than. So really, we want to jump. So what's interesting is we want to jump from the beginning of. So this is going to be interesting. This is going to be interesting how we do this. So I s dot size plus I. We're going to say jump of I equals 0. And then we're also going to say if, so we're going to say constant x is going to be I minus O of I, and y is also e of I. So we're going to find the leftmost value, right, of these the largest palindromes. So what's interesting is for the odd, we actually can see the left side for odd is just I minus k plus 1. So I minus k plus 1 is the left side. That's the furthest character, right, on the left side, the index on the left side. The right side, for even though, it's also I minus k plus 1. And we're going to say jump of x is equal to standard max of jump of x of itself and I, and jump of y, same deal. And we'll say if x is greater than or equal to 0. So this is how we're going to build our jump array. Okay. So this is quite the algorithm at this point. It's taking me forever too, mostly because it's just writing out monikers for me is like, it really takes me a while, or at least how I've been doing it takes me a while. It's a simple algorithm, but it can be really tricky with the indices. You want to get that right, or yeah, you got to kind of practice it, I think. So create our jump array, and we process jump array jumps with minimum process, calculate minimum required jumps. Int ret equals 0. Okay. So the way this works, we're going to set jump to 1. It's always going to be at least 1. And what we're going to do is say x is going to be I minus O of I plus 1. So it's not actually I, it's I plus O of I. And then I plus E of I. So that's a tricky thing. So to the right, it's, said this before, it's I plus X for E, and it's I plus X minus 1 for odd, for O. So this is the, and actually the jump is actually further than that. I'm sorry, it's not exactly that. It's 2 times O of I plus 1. Or even 2 times, I think it's actually minus 1. So if O was 1, then it would be, jump would be 1. If O was 2, the jump would be 3. Yeah. That's the index you're jumping from. X is the index you jump from. And the size of the palindrome is actually how far you're going to jump. Same thing over here. It's actually 2 times E. I did that wrong. So you got to set up the jump table. And I got to process the jump table. So the way you do this is just a for loop and a while loop. So you'd say you have just int A equals 0, B equals 0. You could say B is actually going to be jump of A, or 0 initially, and yeah, and the loop is going to be, it's kind of just a while loop, I guess. And these really could be inside here. A is less than you would say A is less than s dot size, and what you're going to do is you're going to say a while loop or a for loop. You say int x is going to be from A, x is less than or equal to B, plus plus x. And we're going to say B equals standard max of B, and it's going to be x plus jump of x. So at each iteration, we're going to, the way it's going to work is we're going to start with a range. So the first jump we'll process. And we'll start with at least, you gotta have at least one jump, right? So A is going to start with 0, B is the jump, right? That's sort of the beginning. So we do at least one jump from the beginning. Just thinking if there's any other way to do this. Don't think there is. The first partition is interesting. Part of the problem is actually how many jumps do we start with? How far in do we start? Excuse me, well, I think you just need to partition the first value, right? That's really tricky. I don't know what the best starting point would be. I have no idea. I might be doing this wrong. Oh no, there's so many points that this could be wrong. So many pieces of code here. I don't know if the logic is correct. I'm thinking about it. If you have to have an initial starting point. Might be thinking about this wrong. There has to be some first jump you make, certainly, right? Some first cut. And it has to include the first character. So I think it's fair to start at the beginning. I don't know. I wouldn't know what to do otherwise, quite frankly. So there's one cut in the beginning you start with. And then you say increment the next range, and then you say A is going to be, we're going to say next, next equals B. I could say next, oops, next equals next plus x plus jump of x. A is then B plus 1, B equals next. Something like this. And so now you've made your jump, right? And you would increment ret. And jump is always at least 1. So always go, yeah, you processed B at this point, so you can go to B plus 1. I think that works. I think it's okay. Something like this. Let's see how this goes. This compiles. Start with that. Runtime error. Okay. Now, how does that happen? Out of bounds. $16, $17, $18. And then we have an error. Oh, this could be 0. Oh, I see. I didn't think about that. You have I is large and E is 0. So this is kind of interesting. This is, you could do this too. Wasn't expecting that, but the reason for that is kind of awkward. Oh, it's correct answer. Whoa. No kidding. Kind of would like to run through a lot of different tests for this. I think we got it, but oh no. Oh, okay. That's interesting. Oh. Yeah, we just have to say b is less than s.size. Or x is less than s.size. That's interesting. Wrong answer. Oof. Oof. It's supposed to be rep -1, I think, at the end of it too, by the way. I think these are just all wrong. Oh, no. No. I think it's just sheer coincidence we got the last one right. So let's look at AAB. Okay. I got the right answer for AAB. What about A? A should be 0 cuts. We got 1. Well, A is 0, B is jump of 0, which should be 1. A is less than the size, which is 1. Next equals B. I guess we don't have a first jump necessarily. Yeah. Something like this, I don't know. So 0, 0, 9. Something's not right here. Something's not right. Well, ret tells us how many jumps it takes to get off the edge. I think this is correct, but A, B puts us at 0. So if we got 1 jump, so A takes us to this index here, this B. We should get 1, right? So let's just look at AAB. Why do we get 0 instead of 1? What does jump look like, and what does x and jump of x? Okay, let's give that a shot. See how that goes. So I don't think we got the answer. So x0 jump is 2. That's correct, right? That 2 characters. So we would jump. When we jump to yeah, how many characters at that index? So I think it's actually supposed to be x minus 1. We get 0, 1, 2. Oh no, but it's 1 past. Yes, that's correct. So jump 2, and then so that means that next ends up at 2, and the first time around, I think we probably should just AB. I seem to have programmed this incorrectly. I don't know what I did exactly, but I did something silly. How are we doing on time? Hour and a half. So A is 0, B is 2. Okay, so immediately the first jump. So this actually is supposed to be -1, I think. Because the first jump is not supposed to take us beyond. It's actually just supposed to put us inside of the first one. Okay, here we go. 0, 1. And so now we say x0 jump 2, right? So we make that first jump, and we jump to B. And then there's x1, jump also to B. And then from B, A is 2, B is 2. and we jump 1, and we go off the edge. Okay, that's what we're supposed to do. Yeah, that's kind of a subtle thing, but well, actually, both of these we're probably going to need more debugging. So let's not get ahead of ourselves here. Okay, how about the other scenarios? All right, so it's just the last one really that we have an issue with. So we got 10, we expected 11, so we should debug this one. Now this one was the one we had right before. Now it's wrong. What happened? Let's see if we got the correct jump table. I think Monikers is probably right at this point. We spent a lot of time on that. I think the jump table might be the issue and how I'm processing afterwards. So initially, first jump is AAA, right? Then, and we're saying we can do this in 10 cuts instead of 11. That's interesting. It'd be interesting if we got a better solution, a more correct solution. That would be kind of wild. I don't think so, but it's possible, I guess. Technically possible. All right, so x0, jump 3, x1, 5, x2, 6. So we would get 8, right? So we jump to 3 and 8. So we get 0 to 2 here, and then we get 3 to 8. Now, what's interesting about that is 0, 1, 2, 0, 1, 2, we could jump to 6 from here. And why is that? Why does 2 have a jump of 6? Oh, that's because there's this palindrome over here. So that's 1, 2, 3, 4, 5, 6. Oh, that's super interesting. Okay, yeah, because we're jumping entire palindrome. So we can make a cut. Now, what's weird about this is you can make a cut somewhere in between here. I think that's maybe the error that I'm making, is that I'm assuming that all of these are valid jumps, where these are splits amongst different palindromes. So that's super interesting, like where you can actually split the palindromes. I think you technically always could, because no, see, that's a problem. Not every sub. No, this is a wrong algorithm. It's pretty interesting that we went through it and took forever to code it, but it's wrong because not every substring of a palindrome is itself a palindrome. That's actually not true. So this jumping doesn't quite work the way I would like it to. No, we gotta think of something else. Sure, Monikers is still useful here, but the jump routine at the end doesn't quite work, because you really can't jump to all the spots you'd like to jump to. Yeah, not necessarily. So this is referring to like breaking off here, but I mean, it does work. You could put a split here, and then you can go to 8, right? 1, 2, 3, you know, you can go all the way over there. And now you're here, right? You're looking for a way to split, partition this piece. But the problem with that is you get 1, 2, and now you're BC all over here, right? So 3 to 8, you get 9. 3 to 8, you get 9 to 9. So 0, 1, 2, 3. So 3 to 8. 3, yeah, you go all the way. 3, 4, 5, 6, 7, 8. Now that's kind of off too. You 3, 4, 5, 6, 7. It really should be 7 that you process. It shouldn't go It actually shouldn't be b plus 1. Yeah, so I think it's actually next to minus 1 is technically correct. Okay, we need too many now. So this would be something like 3 to 7, right? So 3, 4, 5, 6, 7. Yeah, that's fine. And then the jump from there puts us at 8 and 8. So 3 plus 6 is 9. So that's kind of weird. Wouldn't this be? Yeah, 9. Oh yeah, okay, it would be 9. But then we subtract 1. So 3 to 9. So 0, 1, 2, 3. And here you could do 9, it says. 6? 1, 2. Wait, what? What? Why do we have 6 for 3? That's not right either. 0, 1, 2, 3. You could do. Oh, I think it's because you could do 1, 2, 3, 4, 5, 6. Oh, you. But no. No, that's not 6. I did this wrong. When x is 3, what is EI and O I E-I-E-I-O bum 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 da na 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 bum 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 bum. So Y was 3. So that's 3 routines of 3 even values, and so jump of 3. So here we go. Y of 3 is 3, and E of I was 3. So Y of 3, E of I was 3. What was I? Let's try again. This is going to take a while, huh? I think so. I think so. Oh boy. And little do I know there's some kind of DP solution that's simple. Alright, Y is 3. I don't think so, probably not. So I is 5. Okay. 0, 0, 1, 2, 3, 4, 5. So that's where I is. I is here. And somehow we got even of 3? Oh, yes. 1, 2, 3, 4, 5, 6. Oh. That's at 5. 0, 1, 2, 3. 0, 1, 2, 3, 4. 5? No, that's not right. How did that happen? I think Monikers is wrong. No, I spent so much time on that. I spent so much time. No. 0, 1, 2, 3, 4, 5. And we're saying 5 has E of, that's a 6 character, has 3 even. So, I mean, there's 1 here, 2, 3. I think it's the wrong direction that it caught. Yeah, that's interesting. So, even onion should be I minus k, which is s of 5. You know what it might be? It might be actually this portion. Even onion here, yeah. I think there's supposed to be a -1 here or something. When we're talking about when J is 5. Let's see. I think this is part of the issue. It's gonna happen a few times, but let's see. Yeah, there you go. When J is 5. I think when J is 5, we ended up updating incorrectly. J is 5, X is 3. There you go. There you go. That sounds, well, actually, that's too late. It's already been set to 3. When was that set to 3? So we only update on the even onion is when we update E. I equals 5. I E of I, or just K. K. I is 5, K is 3. Okay, how did that happen? 0, 1, 2, 3, 4, 5. How do we get K is 3? Oh. I think I see what happened. I think I see what happened. It's got to be at least this value. Ah, that's interesting. So when I is 5, X is 2. 0, 1, 2, 3, 4, 5. Oh, I see. Now that's incorrect, right? R minus I at this point, R is okay. what happens in this scenario? I is 5, x is 2, r is 7. Okay. Somehow we get I is 5 and k is 3. I don't know where that came from. Yeah, we're assuming k is... So I think part of the issue is that the way I wrote this, we set k to an initial starting point, which you can kind of assume, but I think we're assuming incorrectly. I think that's why it's wrong, which is like a very subtle logical error, but that's fair enough. But I think part of the problem is how do we get I5, X2, and R7? So that is an issue, right? Like that'll immediately put E at 2, where it should actually just be at 0, right? Like 0, 1, 2, 3, 4, 5. This should just be at 0. I don't know how we got R minus I. Why that's like what happened here. So apparently R is 7. I is, so what happened here? So I is 5, X is 2, R is 7. Hold on. I is 5, R is 7. So I don't know how we ended up in this else statement if, excuse me? What? I is 5 and R is 7. What? Oh yeah, that's fine. No, we're inside. So we're inside. So there's a large palindrome that oversees this whole section. 0, 1, 2, 3, 4, 5. So there's a 5, 6, 7. So there's this palindrome, 3 and 3. This big palindrome. We're inside. We're inside this palindrome. Now x in this instance is actually too small. Now what's interesting is we're inside this. We're not at the right point. Oh no, we're to the right. That's fine. No, that's okay. L, it should be L, R minus 1, minus I. The right side, minus I, J, R minus I means there's 2 characters to the right. So why I plus X is greater than R? Why do I think that there is a palindrome that goes to the right here? There's clearly not a palindrome that goes to the right here. It's part of the issue. What is going on? What? This is a palindrome, but this is not. What do we do with the even palindromes? Okay, so we're calculating this part incorrectly. Who knows exactly why? Excuse me. I think I is in the right spot, but the question is the value on the other side mirrored across, right? So that's what X is supposed to be. X is supposed to be, so we got X is 2. If we mirror across 6, We take a look at J. So J might be wrong. That could be the issue. I think L plus R minus I is supposed to be the right spot, but we get 3, 4, 5, 6, 7, 8. So it's 3 to 8. L plus R is 3 and 8 is 11. And you're saying I plus J. So that might be part of the problem. I think J, when you're looking at even values, is a little bit different. That might be part of the issue. They wrote this really well. Mine is nowhere near as succinct. Things to note: since an even palindrome will have two centers, I is the latter of the two center indices. If I exceeds R, K is initialized to 0. As a single letter is not even an even palindrome. The size of the palindrome center at I is X, then D, 2I stars X over 2. Launch it with respect to the value of K. Oh, I see. So we just always set K to 1, no matter what. If we hit the the ending, okay, that's fine. We don't. I was thinking of trying to optimize slightly, but it looks like it's not worth it, and actually looks like it's incorrect in some cases. This is a lot cleaner than what I wrote. I'll tell you that much. But you can see slight differences. The slight differences that trip me up versus, yeah. All right. I'll probably like memorize this. This is a lot better than trying to do what I did. Yeah, doing what I did is kind of awkward. I think you just always start off at 0. Yeah, you really don't need X to be updated that way. It's okay. It's okay. I think it just causes problems if we do it that way. Oh, now we're correct. Hey, sweet. Let's get rid of all the debug code now. Well, let's not get rid of this. This we might need. Yeah, I'm definitely thinking, or I'm starting to think that I probably should copy what they have for the Monikers algorithm, and like writing it myself is all well and good, but it definitely looks a lot better to run it the way that they did. What did they say this? What did they have to do this? So you always run it no matter what K is. If we're greater than R. Oh no, wait, I'm wrong. They did do this proper. They did it. They did. I'm sorry. No, you do optimize this slightly. You don't start at 1. It'll be correct, but won't be as efficient as it's supposed to be. No, they did this right. It's the minimum of these two. L plus R minus I, or R minus I plus 1. Oh, this is J. Yeah, it's either J or this value, R minus I plus 1. So it's each time it is R minus I plus 1. So what did they do? They said int k or x equals e of l plus r minus I, the minimum. That was a critical part of the algorithm. That was not right. I see. They did things a bit differently, huh? How about this? Oh, wow. It's a lot more succinct, but it's definitely not correct. That is a lot cleaner. So they did it, but it's way wrong, it seems, or it's probably wrong. So is the onion routine I greater than 0 or 0? Try to figure out what I did wrong. I don't know, it's gonna take me a while to figure it out. I is greater than R. Onion I1. That's fine. Decrement 1, so that's a D of 1. I plus K is greater than R. That's the onion part. Does that. Decrement K. Oh, I see. So they actually did it a little bit more clever. So you don't need to do that here. I plus K, I minus K. It's the odd part. The even part looks the same, except there's a minus K minus 1 for the L. Oh, did that wrong. Might have something to do with it. I think otherwise we have the same logic. We're way over though. Boy, okay. So 0 to 2, that's correct. 3 to 7, 3, 4, 5, 6, 7. Just want that to stay highlighted. So 2 to 6 is fine. There we go. 3, 1 I think is correct. 0, 1, 2, 3, 3, 1. Actually, 3, that should be more than 1. That should be way up there. 4 jump. 0, 1, 2, 3, 4. 4 jump is 1. I think that should be at least 2. Oh, no. Yeah, this one should be at least 4. 2. So those are wrong. All right. What are the values we get for O and E? Let's try that. Oh. By the way, this could just be also a ternary operator. This is basically what the other code has. This is pretty much the routine, almost verbatim. Now we just want to debug. Okay. Odd of 0 is 1. Odd of 1 is 2. Even is 1. I think the thing I was wondering about, the thing that looked really weird, is at B, there should be, so 0, 1, 2, 3. 3, there's odd is 3. 1, 2, 3. And even, there's 0, correct? And then 4, there should be even 1. Oh, there's even of 1, 2, 3. Yeah, that's what I expect. Okay. So what happened with my jump table then? I think I got the monikers part okay. I think we got that. I mean, at this point, like, this is almost copy pasted what they have. It's like exactly what they did. Almost exactly. Excuse me. I think the only difference is we had, I think and I should probably do that too, the midpoint for the even values is to the left, s minus k minus 1. Let's do that instead. I think that's better. I think it's confusing if I do it the way that I've been doing it. I minus k minus 1. And yeah, that might have something to do with our algorithm here. We're on the wrong spot with our even portions. So 5, we have even 3. 0, 1, 2, 3, 4, 5. That's wrong. 1, 2, 3. So now our index is to the right rather than on top of it, I think. So its characters to the left. Doesn't really make a lot of sense how they did it. Oh, okay, I is the latter of the two center indices. Well, actually, I wanted I to be the other side. Actually, I had a different way before, which I think was fine. So theirs, they take the right and center. I took the left center. That we can still both be correct and just disagree on that. But the tricky part now is, what does my jump table look like, and why does it look wrong? By the way, I think this algorithm is incorrect anyway. The sum total of what we're doing here, I don't think it's right. Okay, so just the approach is wrong. So jump, so from 3 there's only jump 1, 4 is jump 1. So 3, 0, 1, 2, 3. So there's definitely this palindrome, right? And oh, I see. Because of this palindrome, that palindrome gets ignored. So that's the first issue, I think. This actually might be, the jump table might be set up correctly, and the monikers may be set up correctly, but the algorithm is wrong. And I think that's where we're starting to see that. So yeah, first problem is that you're not going to see this because it's centered here. You're not going to see that. This jump is not a possibility because of so that's really interesting, because we could update. There are a lot of different possible jumps that you could make. I think that's kind of the problem, is that there's so many different jumps you could make for the different palindromes that it gets a little bit awkward, I guess. I think starting with monikers is not a bad call, but usually part of the problem is maybe we could modify monikers. Part of the problem is that this quote-unquote jump table doesn't really make a lot of sense, because for starters, you can jump. There are a lot of different jumps to process once we've built monikers. We can actually add more data to the jump table. That's one thing. Actually, maybe that's all we need. Maybe we just need to modify the jump table with better, more data, like basically all of the possible palindromes that you could have. All those indices, all the jumps, just take the largest possible jump. Yeah, actually that's fine. Maybe I'm wrong. Maybe I'm wrong about this not being correct enough. So let me try that. So what we can do is, actually it's not just we actually, these are subroutines we execute. So for int x equals, or yeah, we'll do say a x t. We just do t is equal to O of I, and t is greater than or equal to 1, and decrement t. We can perform this x is equal to t, I minus t plus 1, and we say if x is greater than or equal to 0, then 2 times t. So jump of x. So we can take all the palindromes that we have that are possible from that point, and update that data. That's sort of the idea here. And do the same thing for e. Just give the same kind of calculation. t is e, I minus t plus 1, and this is 2 times t. And same idea. Also, y has got to be less than the size as well. That's kind of a tricky thing. The reason for that is in some cases, because t could be 0, I think if t is greater than or equal to 1, yeah, t could be 0. If t is 0, then there's nothing to really look at or calculate. So we don't need this part anymore, which is nice. Yeah, so this might help a bit. Still 13. So now we have jump 4 on 3. That puts us further ahead. Okay, that's kind of what I was looking for. So jump 4 on 3, 0, 1, 2, 3. Now we can jump 4 ahead, and that puts us at least at 7. 4 could jump at jump 2. 5 can jump 3, puts us at 8. 6 can also jump 3, and 7 can jump 1. So we can get all the way up to 9. But for some reason we go A is 8 and B is 8. How did that happen? So next we say A is B plus 1, which this B was 7, so we go to 8. And B, oh, it's not, it's next to minus 1. Oh, that's why. I think it's actually just next. I think I might be wrong. So we get x plus jump of x. So we would get, that would be 8 for 7 plus 1. But if we do 6 and 3, 9. If the index is 6, 0, 1, 2, 3, 4, 5, 6, and we get 3 characters, 1, 2, 3. I think it's just that index 9. And so next we can reach all the way to that character. Yeah. Okay, it's a little bit better. Now we're way ahead. So 9 and 9, that's what I thought. You go right to 9 and 9, or yeah, 3 and 8. So am I wrong though? 0, 1, 2, 1, 2, 3, 4, 5, 6 puts us at 0, 1, 2, 3, 4, 5, 6, 7. But 6 plus 3 puts us at 9. 6, 7, 8, 9. Oh, wait. 6, 7, 8. Oh no, I'm sorry. It is next minus 1. I had it right the first time. But why? So I end up jumping to 8, 8, and 8. A is 8, B is 8. Now we say 0, 1, 2, 3, 4, 5, 6, 7, 8. 8 and 8. And then now, excuse me, they're equal to each other. We process here. Next is x plus 1. Oh, I see. Which is 8. So this shouldn't jump back to 8. This should go to the next value. I think next is actually supposed to be b plus 1. Something like that. I don't know why. I think we're doing this wrong somehow. This really would be should be 2 characters, at least 2 characters. And the reason is that you're jumping to the character that you're going to include. So you subtract 1. I don't necessarily know if it's supposed to be next minus 1 or it's just supposed to be the number of characters minus 1. I think it's supposed to be like this. But if you only jump 1 character, then you've got a so next is the same. Yeah, because that's kind of weird. Also, there's been a really a lot of time here. 3, 7. So 2 to 6 puts us at 7. 0, 1, 2 plus 6 characters. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6, 7. Yeah, that's correct. That is, you can jump there, right? And the beginning of the range, the next range we're going to consider, it doesn't actually need to include that spot. That's the thing. What's going to happen next is we're going to set that's the end of the range that we're going to process now. Oh yeah, no, we can reach all of that. We put a split, somewhere previously, and all the things in between we can now reach. And so we just update A to B plus 1, our previous spot B plus 1, and then we're going to reach to next. But what if our reach only extends from the index we're at plus 1 character, right? In that case, we need to update A to B plus 1, and B is just going to be standard max of next and A, I think. So that's just not too far behind. Oh, no, it's correct. Okay. So we need to fix our jump table. So it seems which is a bit awkward, but whoa. Now I guess my question is, how come this jump table seems, jump table algorithm seems kind of like, I don't know, doesn't quite seem right, but I guess it's okay. So I guess what we're saying is we just want to make sure that next is not behind the next range. Well, we're always going to jump forward at least 1 character. It's weird that we had to do this though. That's the thing I'm kind of hung up on, because it lets us know how many characters we're jumping. It's just that it's like if you jump 2 characters, it's fine. You're not gonna, you don't waste a routine behind, so to speak. But you should jump to because next can actually fall behind A, right? A becomes the next character in the range. But if you only jump 1 character from where you are, that's really weird. 1 character, you'd want to go to the next range. 1 character, you don't go anywhere. 2 characters, you go somewhere. That's kind of the deal, is that if we always jump at least 2 characters, I think you something like this. I don't know. A max and a min. I don't know. It's okay. It just seems weird. It feels like I'm doing something wrong. But I guess if it works, it works. So let's try a few other strings. All right, let's just try a bunch of different things, see what happens. I don't think we're correct at all. I think that our algorithm is wrong. Yeah. Okay. Great. 11, 4, 9, 0, 8, 15. So 0, 1, 0, 1, 11, 15. All right. 0, 1, 0, 1, 15. Is it this one? Wrong. Wrong, 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 wrong. Okay. And let's just see if this follows what we expect at least. So we got too many cuts. 0, 0, we jump 1, 1, 1, we jump 5, 1, 2, 3, 4, 5, that's fair. Now we're here at 2 to 5. We say, okay, we're going to jump 2, 3, 3, 1, 4, 1, 5, 1. That's 5 and 6. 0, 1, 2, 3, 4, 5, 6. So we jump to 6, which I think is fine, right? Then there's nothing to jump from except the 7, then to 8, then to 9, 10, 11, 12, 13, 14, 15, 16. I could actually print the characters too, that might be helpful. Like print the substrings. S dot substring of A and the number of characters actually should just be 0A. I'm not sure if that should be part of the jump, like where X is. I think that's where I should do for X. That's clear how far the jump is. Actually, that's fine too. So here we are. We have J, jump 1. Keep jumping, 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 jumping. And then here we have 20. We jump off the edge now from G. So we could put a cut here where G is. So what's interesting is we have 17 and the expected is 15. So what would this look like for us? We were saying we can do S, df, ds, and put a cut here, put a cut there. Okay, wow, a lot of time so far. F, there's no palindromes there. L, K, V, J, B, L, K, J, D, L, K, J. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, and my algorithm came up with 17. How do we get 17? I think it might just be implemented incorrectly, because I think this is a scenario where we should be correct. How are we doing on time? Oh, it's a lot of time. Yeah, I used a lot of time already. First jump to 1, A. So that's 1 now. Next jump is to 6 and 6. 0, 1, 2, 3, 4, 5, 6. All right. Yeah, because the first jump was 2 to 5. So we got 1 to 1, then we get 2 to 5, then we get 6, 7, let's see how we count, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, that's already 10, 10 at 16, 10 plus 2 should be 12, 17, 18, 19, 3, and there's the last one, plus 4. So it's 16, and then we subtract 1 at the end. This is 1 extra jump. We don't need 1 for the last jump. Basically, we assume where we jump, we put a bar. That's pretty much how we're doing it. So this should be 15. We should have the right answer. How did we get the wrong answer? How did that happen? So each iteration, we increment ret by 1. What? I counted I counted I counted 16. I counted the right number of jumps. Like so far, this algorithm actually seems okay. Believe it or not, this seems pretty reasonable. Yeah, this seems okay. The thing that's different about this that may not be correct, like we might run into issues with, even if we get it right, implemented it right, I think we'll still have problems because the issue is the issue is the things we can jump to are not necessarily, well actually no, I guess we're fine. If everything that we're looking at a particular index represents like palindromes, which they are, right? It's just a palindrome that you're going to jump from this part of the left side of the palindrome to the right side of the palindrome. Actually, every break we make is going to be has to be a palindrome. That's interesting. I think we're correct, actually. I think we got it. Yeah. It's always gonna be the largest palindrome you could jump to. I think we did it. I think we got it. I'm thinking for some reason, okay, why is ret 17 here? So starts off at 0. First jump at, so first cut is this one, right? Next cut is 1, 2, 3, 4, 5. Later, second cut is here. So first cut, right, is 1, 1, 1. Second cut, 2, 5. That's fine. Third cut is 6, 6. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. Now, what I'm curious about is we're already at 15. We should stop at 16. And also it's ret -1. There's 2 extra jumps going on here that I don't know where they're coming from. What is that 18? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we get to here. And the problem, I think, is that this is split into pieces. Really should just end here. This should be 19 to, so we're like a jump behind, I think, right? Like somehow we're like 1 jump behind. 17 gives us, oh, I think I know. Well, a couple things. So this is a case where we jumped off the edge. B is 22, so 18, 19, 20, 21, 22. Oh, I see. So if B is if we can jump to the edge, well, we have 1 more jump off the edge. Which we subtract, right? That's the one we remove, is this jump, right? Which is why we subtract 1, because we're here, we could make the jump, we realize that. What's interesting is, it looks like we have too many things that we're adding. It's like, I don't know what's going on. When A is off the edge, then we're done. Yeah. We subtract 1 because we have basically we jumped into this here. Where 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Well, we're looking at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Well, we're looking at 19, we should have like 15. 19 should be 15. 19 is 16. Why? I think it has to do with what I was tinkering before with single jumps. Like, I think it has some issue with single jumps. 0, 0, substring 0. ret 0, x 0, jump 1, increment, first jump, we end up with 1, 1. So, oh, I think that's part of the problem. This is supposed to be, this isn't 2, this is itself supposed to be 1, 1, 5. 0, 1, 2, 3, 4, 5. Yeah, I think that's the issue. This first jump is supposed to be 1, 5. Why did we get 0, 0? I think that's the issue, is that that is the issue, actually. That's the problem. This first, yeah, it's something to do with jumping around. The jumps aren't right. When we make the first jump, like obviously we only have one character we could start with. Like we just have to jump from here to somewhere. So we end up jumping here. But we didn't process how far you could jump from there, that one jump. I think that's part of the trick here, is that even though you can only jump once, this can jump all the way here, and it should. So we have an extra, so our algorithm has an extra line here for some reason. And another one somewhere else, which is probably over here, actually. I think 19 has another one. Something like this. There's some issue when you're jumping to a larger section. Something going on here. Yeah, so we have one here and one here. I don't know where we got this from, but it should be, we jump to the next value, and where we jump from there is, so the first value we jump to 1, which is S, or to the left of S. All right, start off at A, jump to the left of S. Excuse me. A is 1, B is 1. Jump to 2, 5. Or jump to 6. So the first iteration, red is 0. I'm so confused. It's very confusing. So this is wrong, I think. I don't know. I don't know what's going on. I'm so confused. I'm so confused. We're not preparing correctly. So we would make a bar at the first jump. How do we make the first jump? The first jump would be really red equals 1, and A starts off at jump of 0, minus 1. Well, I mean, we can make the first jump, right? That's fine. A is 0. We didn't jump yet. B is the first jumping point. So we make the first jump once red is 1. And now we have A and B are initialized to where they should be. So now A is 0. B, now here's the question though. B should actually have the jump range. See, that's a problem. I think that is the problem. Like that's the brain's starting to mush. What's it supposed to do? It's kind of a breadth first search, so it's a type of breadth first search. So what we're doing is we're saying, okay, let's try to talk about it in English and then code it again because we have the logic wrong here. First thing you do is you make a jump over from A to A's range, right? That's your first jump. And you're going to set up a line, a vertical bar, a bar. You're going to set a bar right after, and that'll be the starting point of your next jump. So that first jump we know is going to be A. So we could even start. We could just make that first jump. We could just start A at the first bar, right? Which is jump 0 minus 1, right? We could just start that. So we could say, you know, ret 1. Oops. Ret 1. Jump 0. That's how many characters, right? So jump 0 is the number of characters. Let's say it's 1 character. So 0 plus 1 gives you 1. And that's our starting index, right? In this case, actually, it is just 1, right? In this case, it is just 1. So we start off there. And we start off B is the range that A jump of A has, right? Now the tricky part about that is we don't want to do that because we have some code to kind of check for conditions. So we could start off ret at 0 and then perform the first jump here. And so we'll set up A and B, presumably properly. So A will end up, after the first jump, we're going to say x is A, which is 0, x is less than or equal to B, which it certainly is. We're going to find out the range that, so this is actually the range of A, how far A can jump. And we actually figure out how far we can jump through the range of A. Now, if we only process A, then it's only really to one element. And then we make that jump by updating A to B plus 1. B is then this minimum. So in our case, B just goes straight to this S value, right? B just, yeah. So where does A go? A ends up at B plus 1. B jump 0 minus 1 is actually 0. That's kind of interesting. Is that supposed to do that? Yes, because it's an index. Yes, it's the number of characters plus 0 minus 1, right? That's an index. So really A can only jump to itself, and so we have to update A to. So next is B, which is 0. A is B plus 1, which is 1, and then B is then 1. Now, what's interesting about this is the next jump is not set up properly, because now we look at S and see where S can jump to. So we jumped to S, jumped from A, we jumped to S, used 1. Now S can jump really far, can all the way jump all the way to F. So one jump, ret 1, was to S, behind S. But the problem is that this next jump is not going to jump all the way across. it's actually just going to jump from S to S. And now that's really weird. Now, why is that the case? The reason is our first jump doesn't take us to S, or it takes us to S, but it doesn't give us the range that S has. It doesn't process S, which I think is the part that's really confusing. We didn't process S for some reason. S itself can jump all the way to F. Now ret would have 1, 2. Ret should have 2 after we jump, not before we jump. And that's I think that's part of the problem. I think that might be one of the things we're doing wrong. And it's so confusing because I'm trying to wonder. I mean, maybe it's not wrong. Maybe I just think it's wrong. I don't know. I don't get it. I'm struggling, man. I'm struggling. It's also getting really late. I wanted to solve some other problems, but this is such a challenge. Why? Okay. So we get a first. This. It's code. I want to eat some food. I want to go sleep. I want to stop. I need a break. Shouldn't say I do that too much. So the number of characters you can jump from A is just 1. That should be fine, right? Start off A at 0. We jump nowhere because we only go 1 character, which means we need to artificially jump ahead. But the problem there is that it seems that we put another bar in front of S here to process S and figure out how far S can jump. We don't already know how far S can jump. I think that might be the issue. Which is really, really weird. Yeah, we take an extra step to process S. Now that's really odd. I think the range should actually be, I guess the range should already be updated with the value for S. So that way we would just jump to S. Because we jump 1 jump to A, 1 jump to S, it's 2 jumps, and the 3rd jump to F. So it's 3 jumps. Yeah. And we subtract one of these. We actually should subtract 2, right? We should subtract the first one here, this first one of these jumps, this first jump getting ready. There's also another jump at the end that we have to subtract. So there's actually 2 jumps we need to take away. I think that's the problem, right? There's 17, but we got to subtract the first jump from the beginning, and there's another jump at the end. There's actually like 3 jumps. There's 3. There's all these extra jumps going on, man. Like, what is happening? Excuse me. We don't initially process A. I think that's part of the problem. And the reason why we don't initially process A is because it's awkward, right? Because if A doesn't go anywhere, yeah, it's awkward. Once A jumps to S, S should immediately jump. So I think that's part of the problem, is that we're jumping to S on the right side. We're jumping on the S on the left side of S, or the right side of S. Rather, we're putting a bar to the right of S. There should be a bar to the left of S. There's a bar to the left of A bar to the left of S, and then it should be a bar to the left of F. So that should be the 3 jumps, 3 bars. That's correct. That is what we're doing. It's just, it gets confusing. And then I think what happens is we end up with a bar to the left of GFFG. So let's actually print at each index all the bars that we see. So we could say test plus equals a bar plus wherever A is, so all the characters substring wherever A is to the number of characters, so it'd be B minus A plus 1, I think. Something like this. I don't know, man. It's so confusing to try to figure out what's going on here. Okay. Yes. This is what I think happened, right? So we have 2 extra bars. We have 1 on the left side, which we subtract normally. We have 1 to the right here and 1 to the right here. So the 3 extra bars are 1 here, 1 here, and 1 here. That's exactly what I suspected. All right, so my jumping is just it's not jumping correctly. Like I just screwed up the jump. This one on the left is supposed to be fine because we subtract it, right? It's the one on the right that's a problem. These two. So we get to G. So when we jump only 1. Part of the issue is that we didn't process the thing in front of us. So I think our jump is always supposed, like, I don't know if we do this, what happens? There's something weird going on with how we're jumping. So now we're jumping too far when we do jump, and we still have this before this S. So this is not really the issue. Like if we added 2 or something, just make the jump table crazy. No, that's not what it's supposed to do. I don't know why making this jump table align. Processing the jump table correctly and then making it align with the processing this jump table correctly and then also making it align with the palindrome jumps is really a challenge. Why? I'm trying to do this from memory. It's difficult. So part of the issue is here. So when we jump to A, we say jump to A, put a bar to the left, and our jump from A is only going to go to S. So then we jump to S, and we would process S. Now, when we process S, we should end up with, so 1 to the left of A, 1 to the left of S as we process S. We should jump, so this goes 2, 6, right? A, 2, 6, how do we, so this is the beginning of ret, right? So ret is 0 initially, 0, 0 initially, ret is 1. Once we're at, right, so ret having 1 means we have a bar already to the left, and we're at 1, 1. Ret should tell us how many bars we've placed. Ret should be equal to how many bars we've placed. Something like that. So actually, so part of the extra bars, so there's actually 1 bar we remove at the end. There is an extra bar at the end that we would add. We've already subtracted that. So there are 2 bars that we have too many of. I think actually it's supposed to go to the right, the bar. I think that's a more accurate way to put this. Maybe that's the issue. Maybe I just would like it to be on the left side, but it's actually on the right side. Yeah, because there's no bars when you're processing A. Then you get a bar to the left when you process S. This is the issue, is when we're processing S, something weird goes on. Same thing when we process G. Like, I don't know why we put a bar to the right. Yeah, that is the issue, actually. Process A, put the right of A, jump to S. Process S, put a bar to the right of S, jump to F. Or no, excuse me, we jump to... Yeah, this is super weird. I don't know what's going on. I don't know why... What? What do we expect to see here? We expect to see 0, 0, process A, realize we can only go 1, process S. We can realize from S we can go all the way to F. For some reason, I guess S only goes to D? See, that's really weird. We do 1, 2, and it should go all the way to F. One process, realize we can go to S. 1. I'm so confused. I don't get it. The visual is like not lining up with what I think is supposed to be happening. So you start at index A and you have B minus A plus 1 characters. How about that? Try that. Just do that at each iteration so you know what like A and B is pointing to. So A, S, DF, DS. So that's really interesting. We do process DF, DS in one piece. Because we say, well, we can jump from S. We actually should skip this altogether, right? No, that's not true. That's really confusing. I think maybe it's just a logical thing that I'm struggling with. Like, we process A, we know we can get to S. We process S, we know we can get to F. Why don't we just jump right to F? No, we know. So confusing. This should be A, and then S, DF, DS. It should be the next piece here. That's the same problem we have down here. G and FFG end up being split into two pieces. Now, why would that be the case? Well, A, we know there's only one character, so we put a break to the right of it, and we jump to the next thing. The next thing, we can jump all the way to F, and I think we should. So let's reimagine how we can do this. So A, and we continue to use the debugging code. Oh man, this is killing me. This is brutal. I need to sleep. I mean, I'll just stop, make a part 2. I don't know. I feel like I should be able to do this, but just for some reason I'm really struggling. With process A, we should set up S all the way across. So after we process A, we see that we can get to B plus 1, but we don't realize we can get all the way across. So I guess we process the next character in the next range. I think that's really what we should be doing. Is we should say, here's the range that we can get to. So the index we can get to from A. Oh, I think that's part of the problem. Is that our jump is sort of always like one character. I don't know. Can we just do this? What if we did this? AS. No. That's as far as we can go. It's just A. It's closer, but still wrong. When we process A, we realize we can only jump to S. Feels like this is not the right algorithm, not the right approach. Part of the issue is that A can go to S, but S can go all the way to F. I think we are supposed to do +1 for the jump. What is going on, man? Oh no, this is wrong though. We get other test cases wrong though if we do it this way. All right, so what's happening now? So AS, we know we can jump to S, but this should actually be substring B minus A, and then plus S substring, or really it's S of A plus B minus A plus 1. How do we do this? It's B minus A plus 1 S of B, I think. How about that? So this is what we're, there we go. This is what we're supposed to get. Oh, wow. Excuse me. think I just did it wrong a bunch of times. I think I've just been doing it wrong. Okay, this is what we expect to see. This is what we want, right? And we subtract 1 at the end for this last iteration. Yeah. What about some of the other test cases, though? It's like a whole bunch of these failed, or some of these failed. So which ones failed? The first one and the last 4. So the first one and the last 4 failed. Okay, let's take a look at those. So we make one test case works and the other ones fail. Okay, why might that be? Why might that be? So what's interesting is that some of these do have an ending bar at the end here, and some of them do not. So that's kind of a tricky thing. If you look like at AAB, we subtract a bar, there's no bar at the end that we add. So how do we know we need to add or subtract that extra one? We can start with that. That specifically seems to be, I guess we're processing this next character always, right? For the next range. So what happens is we make this jump, we get AA, so our jump for A is AA, we jump to, so 0, 1, 2, we jump to B is 2, process all of this, and we say, oh, we can jump right off the edge here. I guess if we have, if B is the last character, then so really we get jump 0, 1, 2, jump to B, which is what we want, and then we're done, because as soon as we update where we can go from there, we can go right off. And so we actually update here. And what I would say is if A is greater than or equal to the size, we can increment 1 more. So what is A and B here? A is 0, B is 2, 0, 1, 2. Red is 0. Red is 1 when this exits. And the reason we exit is A and B is just, it just goes right off the edge. So we can jump to the last one. We don't want to go to the last one though. We actually want to go, I think we want like this. We're not just trying to get to the last, we're trying to get off. We're not just trying to get to the last, what's that called? Character. We're trying to get off of the, out of the array altogether. I think what's tricky about that is if we do get to the last character, we need to add 1 more value to denote this extra decrement that's supposed to be there. So I think if B, so let's just print A and B here. It's exhausting. A is 3 and B is 3, so 0, 1, 2. So these are actually the size. Yeah. So if you jump off here, the tricky thing is, it's not so much jumping off here as much as it is B just automatically being at the end. Yeah, it's a little bit confusing. That's really confusing. Something like this. Corrected a few of these. So I corrected the first one, but I think the logic is broken. I think there's just something wrong with what I'm doing. Otherwise, so I should have fixed the second one, which I think it did. So 9 and 4 though are, so these two. Yeah, so what's interesting about these two is these, so these ones. I think these end up being broken up in the way we would expect. 7, 3, we expect 9 and 4. 1, 2, 3, 4, 5, 6, 7, 8. And we would subtract 1 to give us 7. So these are not palindromes. There's part of the problem. Yeah. And this part's palindrome, but this is not palindrome. I think we need to take a break. Something we're doing wrong. We have to figure out, like, the logic we're doing to split into palindromes is not correct. We could just rewrite this instead of using trying to use a jump table, or we can use the jump table, but we programmed it incorrectly. Whatever we did that wrong. I kind of want to go to sleep, but I think we probably could. So we could do it this way. We could just say for there's some int I equals 0, I is less than size, increment I, and we can say first we're going to just update if, so we'll say I, if, yeah, we'll say I plus equals jump of I, and we're going to say ret, increment ret, and the idea is going to be, I don't know, can we do this? What does that give us? We could have a, what does this do? Test plus equals, we'll have s.substring plus another with a bar of, oh, we would do just int temp, substring of temp to I minus temp plus 1. How about that? What does that look like? Oh. Oops. So that's wrong. Maybe subtract 1, I don't know. A, B, C, B, C, A, B, A, C, B, A, C, A, B, C, A, B, C, A, B, C, A, B, C, B, A, C, B, A, C, B, A, B, C, A, B, C, A, B, B, A, C, B, A, B, C, B, C, B. Oh, here we just subtract 1. Oh, that's correct now. Okay. Is this correct in general, or this is kind of the idea that I had, but it just wasn't working properly. It's doing something funky with my jump tables. Some of these look right. Some of these are not right though. So these are at least palindromes, but they're not the optimal palindromes. That's the problem, is that there could be a better, basically there could be a better jump that we could jump instead of just the most immediate jump. Oops. That was what that other algorithm was supposed to figure out, was which of the jumps that are available to us, which one's the best. Yeah. So what do we, which one of these is wrong? 12. So 1, 2, 3, 4. 4 from the top. 1, 2, 3, 4. This one. Ah, yes. The first ones that we had issues with. Oh, I keep hitting the bookmarks bar. That's what that is. Also, I think we just made our cursor gigantic. I didn't realize we did that. Okay. Oh, it's taking a while. I feel like I'm so close though. So output 12, expected 11. So I think the deal is we could have done a much bigger jump. Instead of jumping 3 here, we could have jumped 2 and then 1, 2, 3, 4, 5, 6, right? And then from that 6, then we do B, C, S, D, F. All of those things would have been the same. So how do we choose which jump to take? Well, we can look at all of the things that we're jumping to. Right, so here it's 3. We can have A and B. Oh boy. A starts off at 0. B starts off at the first jump of 0, -1. Right, all these indices. And what we can do is we could say for each of these indices, so that's from, yeah, each of these indices, we'll just say int x, x less than or equal to b, there is a larger value furthest. Furthest out that we can go, which we're going to say is, first we're going to say it's just A plus B, right, or A, yeah, you can go, the furthest you can go would be here, right, to B, which is going to be, I guess A plus B plus 1, something like that, or really it would just be B plus 1, I think. Right, that's just going to be the next, right, this is 0, 1, 2, 3. This jump I minus 1 was, yeah, 3 minus 1 is 2, so 0, 1, 2. So add 1 to that. In this case, it's B plus 1. Furthest point we can go plus 1. So that's the furthest we can go. If we just take A as it is. But we can go through each value of A, and we can update furthest to the maximum of itself. And any value, it's going to be x plus jump of x, right? All of these values in between, we can jump. We can make our jump at this A if we wanted to, or we can make the jump earlier. Because if we make the jump earlier, we actually get one more character, right? We can do A B A B A B and jump immediately and skip one jump, right? So that's the idea. And so we have this furthest value that we can jump to. And depending on which one that is, that's where we want to put our that's where we want to put our where we decided to make our jump. So temp of I, we say, in this case, our jump is actually going to be 2A. It's going to be double A. We could do something like this if we wanted to. Say new jump plus jump of x if new jump is greater than the furthest. And we can update the furthest to the new jump. And we can say int or where. Let's say int temp starts off at A, say temp equals furthest, or no, equals X, right? So that's the value that we used to jump the furthest. And now we can say I plus equals the jump to get to X. That's what we're going to use. The jump that we got to X with is actually plus equals jump of X, I think, or temp. That's the jump we end up using. So before we were saying jump of I, but jump of temp is what we're going to update I to. It's actually, we're going to update A to that. And so I got to think about this for a second. What do we print? What do we do? Uh-oh. The brain. We're not incrementing I anymore. I have something of a while loop here. Oh, maybe that's what I was doing wrong. Is I had a for loop here, so I was probably incrementing things I wasn't supposed to increment. That might be why things got so confusing. That's probably why. Oh boy, that's good. It's always good. So it's not I anymore. It's S, I think, or A. Excuse me. So now what we're going to do is jump. So now that we pick the furthest that we can go, we pick some point, some index that we want to create our bar here after that index. That's temp, and that's going to be A minus temp plus 1. All those characters, so it's going to be starting at temp, yeah. And then A is going to jump to, excuse me, A is going to jump however many characters. I think that's it. And then increment ret, and B gets set to jump of, now what's interesting is I think B ends up at the furthest. Well, yeah, I mean it is. So that's where A ends up going to, and then B ends up set to the furthest, which is also would be, so this is new jump. We set A equal to, we want to jump to, A actually jumps to the value that we found. A actually jumps to temp, believe it or not. One past it. Yeah. So A is going to jump to, instead of jumping to BAAB, it's going to jump to, temp, we said 2, so it's going to jump to A. And B is going to go all the way to the end, the new jump. As far as it goes. I think so. And then now we print we're just going to call this Q. We're going to start from Q and go to A minus Q plus 1. That's really confusing. This is, I don't know what's going on. I don't even know if this is going to terminate runtime error. Okay. Alrighty. So that's not what we want. A, B. So it's supposed to be A. Oh, my brain. Blech. So I started adding this range for A and B. It just gets so confusing. Okay. I think this is this too. I don't know. It's really messy. We're trying to get AA first. So the jump is 0, 1, 2. The furthest you can go on this guy, A, that's the furthest. So what we want to do is put a split between A and A, 0, 1, 2. And what that would look like is, how do we get that furthest jump? Well, the furthest, we could start with B plus 1. That's just 0, 1, 2, 3. Could set that to -1. And then we said A, just Q starts at A, temp start at A as well. If we get the new jump, it's from X jump, so so our furthest we can go would be if we jumped from A somewhere, which you can't go very far, right? That's actually the same thing. We're already processing that. I guess this would have to be A plus 1, really. So anyway, now we can go to, so we get some furthest jump, which really should be, the furthest we would go is oh, hello, we back? I think we're back. I'm gonna turn up the volume and start whispering here instead of speaking so loudly. My brain, dude, it's starting to mush. There's too many variables. There's too many things I'm trying to do. I can't think straight. Okay, let's try again. So X really could just be at A plus 1. With Q, we have temp. These are just variables we want to use. We want to save where we started with A. We're not. This is going to start at A, but it's going to jump to. It's going to jump to whichever value of X that we used. That would get us further. If we were to use that, so we would have a palindrome at that point. Now, a couple issues here is like, one, getting to that point may not necessarily be a palindrome, which is kind of an issue. Realistically, we can only use the that's kind of a tricky thing. These possible jumps that we could use, these have to also be palindromes. So I think that's a test case that we're missing, or part that we're missing, an issue that we're having. Otherwise we're in good shape. But before that, we should be able to at least have something of an algorithm that works. So now we have our new jump. If it's further than the furthest so far, then we're going to say, okay, we're going to use that particular jump. Now, this should be less than or equal to B. So we can go 0, 1, 2, 3. No, the initial jump is 3 minus 1 is 2, so we go 0, 1, 2. So we can go 0, 1, 2. This part, 1, 2, 3, 4, 5, 6, that is the one we should end up using. So we end up using x. It's actually, it would be, that x is where we want to, I guess, jump to. And a is not going to be, it's actually going to be x. We're going to jump to that. And we're going to say b is the furthest, so this is as far as it can go. 1, 2, 3, 4, 5, 6. Plus x, which is 8. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So we can go all the way there. Just sort of, I'm not sure if it should be jump minus 1. Again, I actually don't know. We can't actually get to that spot. We can get close to, we can go right before it though. So I don't know if we should just subtract 1 here. I'm not sure. And then finally, we're going to take A, subtract Q where A was. Now A is updated to a spot. Subtract that. Add 1 to get all the characters and print this substring. So hopefully that gives us something a little bit closer to what we're looking for. Whoa. Wait, what? Uh-oh. Maybe this should be A. I don't know. I don't know, man. Who knows? Just TLDs. This is so funny. A just stays at 2, B just keeps going. Oh boy. Okay. So A goes this spot, right? 0, 1, 2. And then now we jump to B is furthest, which is 8. So we get 2 and 8, and it just goes to 2 and 9. So now, furthest is 9. Start off at 2. X plus jump of X, all these jumps. We say if the new jump is greater than the furthest, then we update furthest. I guess we could say greater than or equal to furthest. I don't know how we end up. I don't know. I don't know. This is a mess. This is so funny. Still TLEs, but at least we get further here. Oh, we're supposed to exit if A is less than size, or B, and B is less than size. Yeah, I guess once we go over, then we terminate. Alright, still incorrect, but a little bit better. Oh, we got 10, okay. So this is, let's get the first one. So 3 A's, A, B, B, A, B, A, B. Okay, no, It's not what we were expecting initially. We were expecting initially to have temp -1 should be, or something. I don't. It's so confusing. This is more what we're looking for. It's supposed to be AA, ABA, ABA. That's what we're looking for. AA, ABA, ABA. There's 4 A's here. Why are there 4 A's? Only supposed to be 3 A's. Where are all these A's coming from? What? So Q is initially here at 0. We're trying to get A minus Q plus 1. A is this new temp value, which it should be. I think we don't include this value actually, where A ends up being placed. Yeah, there we go. ABA, ABA, BC, SD, FB, ADK. There we go. That's what we're looking for. There it is. So now the question is, are these what we expect? And somehow we had too many, or we didn't have enough or something. So we have 1. One, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then we just got rid of the last character. Use that last character. So what happened there? What happened there? Yeah, so last character's just gone. See you later. A is temp, B is furthest. So that's kind of interesting. So this somewhat works. It doesn't do what it's supposed to do, but it's a lot closer to what it's supposed to do. At least we got this part correct, but now we have to finish off at the end. So what happens? Well, we set, what is the last value for A and B? Let's do this. Initial, final. Oh. You get 0, 2 is initially, and then we have 2 to 8 is the next, and then we have 8 to 9, 9 to 10, all the way to 16 to 17, 17 to 18 is initial, 16 to 17 is initial, and 17 to 18 is final. Mm-hmm. Zero. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So this is this value is the 17th, this C here. This one A is 17, and B is off the edge. I think you can do this. Well, we don't have to do that, but we could say We just want to process one more for A. So now A is furthest is B plus 1, which would be 19. Q is A, temp is A, X is just exits. Oh, I see. What's interesting is we basically need to process one more palindrome at the end here. Oh man, we're spending so much time on this. I think I have to make this a part 1 and just go to bed. This is killing me. It's too much. It's way too much time, way too much tinkering with this. Making my brain melt here. When B is off the edge, you could stop. Now, the problem with that, though, is that even though now we can get off the edge, we're missing one execution at the end here. What would that look like, that last execution? Well, what happens if we do this? Well, it's just going to loop infinitely at the end. Yeah, it just keeps going. A doesn't change, and B just keeps incrementing. Excuse me. Yeah, this is kind of half-baked. I really don't know what this is supposed to look like exactly. I'm just kind of tinkering with it until I get something that looks right, which is not the way to do things. So I definitely need to stop and go to sleep. Come back to this later. This just needs to finish. I guess the problem we're having is we're not printing the last characters for C. We get to 17 and 18 to set up for the next loop. But this loop just exits completely. We could say, well, if the furthest is already over, we could do that, but we actually want to push this one over the edge too. This has to go off as well. And when do we do that? Well, we could do that here. Something like this. Something like this. So this is just pretty much just A and then until the rest of the string. Okay. That's what we're looking for. Now, is this correct? I don't think so. Definitely not. Definitely not. So this is what we want. Yeah. Almost certainly not correct. Boy. Yeah, okay. I need to go to sleep. I had an idea about what to do, but it's not correct. Look at there's AAB, B, and then AAB, and oh, what a mess. Putting the bar in front first, and ZZZ, and Z with 2 bars. Oh, these are all over the place. Look at this. Look at this. Brother. Oh, what a mess. What a mess. So this AAB is wrong, right? It should be 1, not 3, 2, and then this should be 0 instead of 1, and this should be 1 instead of 2, and I don't know where are these bars in front coming from? How's that happening? I don't know about that. I guess if the furthest you can go is yourself, then you don't go anywhere. Yeah, that's interesting. So it shouldn't be itself, right? It should be that's really interesting. This one is just wrong. I mean, these are all wrong. How do we write code that handles all these different cases? I don't know. I don't even know what I'm doing to try to get the right answer. I mean, I'm just trying to get the processing to process each case, but there's some algorithm that I need, I think, to properly break this up into the right palindromes. Yeah, it's tricky. It's tricky. Again, you can do this, in theory, you could do this iteratively using like a jump game type of thing, but I don't think it works the way I think I would like it to work. It doesn't quite do what I'd like it to do. So anyway. Yeah. I think I should go look at how the jump game is supposed to work. To do it iteratively, that's 1, and 2. I think this might be a different algorithm altogether. Something about this is a little bit special, a little bit different. I was kind of hoping to be the same thing. I thought it would be very similar, would be the same thing, but clearly it's different and not what I think. And yeah, I should probably review the jump game, look at that, and then come back to this and see what's different about this. Why this doesn't work properly. I don't think it's a jump game. I think that's the problem. I think I need to write an entirely different loop here. Yeah, I gotta think about it for some time, I think. Something like that. I'm gonna go. Thank you for watching. I'm gonna make this, oh boy. Oh boy. Wow. That was rough. Make this a part 1 and come back to this later. So yeah, thank you again. Talk to you soon. Have a good rest of your night. Take care. We'll pick this up sometime tomorrow.